You're standing at the stove on a Sunday morning, pressing yesterday's leftover bacon strips into a hot pan. The fat sizzles and pops. The edges curl up toward the center. You flip them and press harder with the spatula because crispier is always better. That's just a law of bacon. The smell moves through the whole apartment. You slide the strips onto a paper towel, dab them once out of habit, and transfer them to a plate next to your eggs. You pour coffee. You sit down. You think absolutely nothing of it. Here's what's actually happening in that pan-processed meats. Bacon, sausages, hot dogs, salami, ham, pepperoni all contain a class of preservatives called sodium nitrite and sodium nitrate. These are not incidental additives. They serve a genuinely important purpose. They inhibit the growth of Clostridium botulinum, the bacterium responsible for botulism, one of the most lethal toxins known to science. Nitrites also stabilize the pink color in cured meat and prevent fat from going rancid too quickly. Without them, a lot of the processed meat in your refrigerator would be actively dangerous in a completely different way. But here's what changes when heat enters the equation. When sodium nitrite is exposed to high temperatures, particularly during frying or grilling, it converts to nitrous acid, which then breaks down into a highly reactive compound called nitrous anhydride. That compound reacts with secondary amines, which are naturally present in protein-rich food as byproducts of amino acid degradation. What they produce together is a family of chemicals called N-nitrosamines. The two most common and well-studied are NDMA, N-nitrosodimethylamine, and NPYR, nitrosopyrrolidine. Both are classified as potent genotoxic carcinogens. They enter the liver, get metabolically activated by cytochrome P450 enzymes, and then covalently bond to your DNA. That's not a metaphor. The molecule physically attaches to the DNA strand and causes structural mutations. What makes it different from just eating cold deli meat is that the nitrite to nitrosamine conversion requires thermal stress. Below about 120 degrees Celsius, the reaction is slow. Above it, especially during repeated high heat frying, each cycle pushes the reaction further. Bacon's particularly high fat-to-protein ratio makes it worse than other cured meats. As those fats are repeatedly heated, they oxidize, generating free radicals that accelerate the nitrosation cascade. A study on sausage processing temperatures found that raising the cooking temperature from 90 degrees to 130 degrees Celsius alone caused NDMA levels to increase from 3.68 ning-GG to 641 ning-GG, nearly double. That's from a single temperature change. Every time you refry that same leftover strip of bacon, you're not just reheating it. You're compounding a chemical reaction that was already in progress. The FDA and USDA set a regulatory limit of 10 ng-GG for total volatile nitrosamines in cured meat products. That limit exists precisely because this reaction is confirmed to occur and the compounds have a confirmed cancer mechanism. There's also a specific twist with bacon that isn't true of most other cured meats. The smoke point of bacon fat is relatively low, which means during high heat reheating, you pass the smoke point quickly. When fat burns, it generates additional reactive compounds that layer onto the nitrosamine problem. The darkest, crispiest parts of reheated bacon, the parts most people consider the best parts, carry the highest concentration of these compounds. The thing that smells the most like bacon is chemically inseparable from the thing making it worse. Cooking it once, eating it fresh at moderate heat, the risk is real but low. Reheating yesterday's leftovers at high heat until they're extra crispy, you are running a nitrosamine synthesis experiment in your kitchen. And the result goes on your plate: French fries. You ordered takeout last night. The fries were good, crispy, seasoned, the right amount of salt. This morning there's a container of them in the fridge, slightly limp, slightly cold, already past their best moment. You could eat them cold, but cold fries are a miserable experience, so you throw them in a hot pan with a thin layer of oil, press them flat, and give them a few minutes. They crisp back up. You're satisfied. You eat them standing at the counter. The chemistry that just happened is not the chemistry you wanted. Acrylamide is a small, water-soluble molecule, chemical formula C3H-CHNO, and it forms through what's called the Maillard reaction. The Maillard reaction is the same process responsible for the browning of bread, the crust on a seared steak, the golden color of roasted coffee. It happens when reducing sugars, glucose, fructose, react with a free amino acid called L-asparagine at temperatures above 120 degrees Celsius under low moisture conditions. Potatoes contain both reducing sugars and L-asparagine in relatively high concentrations. When you fry or roast potatoes, the surface dries out, the temperature climbs above 120 degrees Celsius, and the Maillard reaction runs. The browner the potato gets, the more acrylamide is produced. Here's where reheating becomes a compounding problem. The original deep fry already created a baseline level of acrylamide. The fry went through the reaction once and came out with a measurable concentration of the compound. When you reheat those same fries in a hot pan, or an oven, or an air fryer, you're applying additional dry heat to an already partially dehydrated surface. The moisture that remained after the first cook gets stripped away. The surface gets hotter, drier, and more reactive. The Maillard reaction runs again. The acrylamide concentration increases beyond what it was after the original cook. The darker and more golden your reheated fries get, the more acrylamide they contain. The ones that go brown or black are carrying considerably higher concentrations. This isn't theoretical. Food safety agencies in the UK, EU, and US have all quantified acrylamide levels in fried potato products and issued guidance specifically warning against overcooking. Once acrylamide is ingested, it doesn't stay as acrylamide. Your liver metabolizes it into a compound called glycidamide, a reactive epoxide that forms DNA adducts, meaning it physically attaches to DNA strands and causes mutations. Animal studies have confirmed that chronic oral exposure to acrylamide induces mammary tumors, thyroid tumors, and testicular tumors. The International Agency for Research on Cancer classifies it as a probable human carcinogen. There's also a counterintuitive storage detail worth knowing. Potatoes stored below 8 degrees Celsius, which includes a standard refrigerator, undergo something called cold-induced sweetening. The starches in the potato partially convert to reducing sugars to protect the cell structure from cold damage. That means cold-stored leftover fries, when reheated, actually have more of the Maillard reaction's primary fuel than fries that were never refrigerated. Storing them cold to keep them fresh inadvertently increases the acrylamide potential when you reheat them. Soaking raw potato slices in water or a citric acid solution before initial cooking can reduce acrylamide formation by 40 to 75% by leaching out free sugars and asparagine. But that's not available to you when you're dealing with already cooked leftovers. The fry itself is not dangerous. Potatoes are fine. But the specific combination of their sugar and amino acid content, heat above 120 degrees Celsius, and low moisture creates a chemical reaction that gets more intense every time you apply dry heat. Golden is acceptable. Brown is a warning. Black is a chemistry event you're about to eat, fried chicken. Leftover fried chicken is one of the great leftover experiences. Cold from the fridge, it's already excellent. Reheated in a pan, it comes back close to its original form. Reheated in an air fryer, it's genuinely competitive with the fresh version. This is a food people have strong and well-reasoned opinions about. And because it seems so sturdy, so clearly cooked through, it's easy to assume the risk calculus is simple. It's already cooked. Just heat it up. Nothing complicated is happening. Something complicated is happening. The hazard with reheated fried chicken isn't the chicken itself. It's the battered coating and the oil it traveled through. Restaurants commonly reuse frying oil across dozens or even hundreds of cooking cycles. Fast food operations, local restaurants, street vendors, the economics of cooking oil make reuse nearly universal in commercial settings. Each heating cycle pushes the oil's unsaturated fatty acids through a process called thermal oxidation. The polyunsaturated fatty acids in vegetable oils, which are the oils most commonly used for deep frying, including soybean, corn, and sunflower, have multiple double bonds in their carbon chains, each one a point of chemical vulnerability. Under heat, these bonds break. The fatty acid generates a lipid radical, which reacts with oxygen to form a peroxyl radical, which pulls a hydrogen atom off an adjacent fatty acid and creates a primary lipid hydroperoxide. At the cooking temperatures used for deep frying, 150 degrees Celsius to 180 degrees Celsius, these hydroperoxides decompose into alkoxy radicals, which undergo further fragmentation into secondary lipid oxidation products. The most significant of these are reactive aldehydes: 4-hydroxy-2-nonyl or 4-HNE, malondialdehyde, MDA, and acrolein. These compounds are classified as potent electrophilic alkylating agents. They bind to the sulfhydryl groups of cysteine, the amino groups of lysine, and directly to DNA bases, forming mutagenic cross-links. The battered coating of fried chicken absorbs the oil it was cooked in. By the time a piece of restaurant chicken reaches your plate, it's carrying whatever oxidative state that oil was in, accumulated across potentially dozens of previous uses. Reheating it at high heat, back in a pan with more oil, or in a fryer, adds another oxidation cycle on top of an already degraded lipid profile. Research published in the British Medical Journal linked consumption of food fried in repeatedly heated oils to a 68% increased risk of cardiovascular events. That number comes from epidemiological data, meaning actual human health outcomes, not just lab models. The mechanism is aldehyde-induced damage to arterial walls and accelerated plaque formation. It's also worth knowing that 4-HNE, once absorbed from the gut, can cross the blood-brain barrier. Studies have linked chronic dietary exposure to it with increased neuroinflammation and elevated Alzheimer's disease risk. Not from a single serving, but from repeated, chronic consumption over years, the chicken itself, the muscle meat, doesn't undergo carcinogenic transformation during standard reheating. That's a separate story involving high heat charring and HCA formation. The story with fried chicken is specifically the coating and the oil it's saturated with. That coating acts as a sponge that captured a degraded chemical environment and brought it to your plate. Reheating in a microwave preserves the chemical profile as is. It warms without adding oxidation. Reheating in a pan at high heat adds another round of degradation. The method matters as much as the food. Reused cooking oils, soybean, corn, sunflower. Here's a practice so ordinary that most people have never examined it. You fried something last week: chicken, vegetables, dumplings. You poured the oil back into a jar or left it in the pan with a paper towel over it. A few days later, you used it again for something else. It smelled a little different, maybe a shade darker. You kept using it. Eventually, it started to smoke too quickly, and you threw it out. That oil was not the same substance at the end as it was at the beginning. Soybean oil, corn oil, and sunflower oil, the three most commonly used vegetable frying oils, are high in polyunsaturated fatty acids, PUFAs. PUFAs are structurally vulnerable to oxidation because of the number of double bonds in their carbon chains. Linoleic acid, the dominant PUFA in these oils, has 2 double bonds. Linolenic acid has 3. Each double bond is a site where oxygen can attack, initiating a radical chain reaction. The autooxidation process works like this: heat, light, or transition metal ions. Trace amounts of iron from a pan are enough. Strip a hydrogen atom from a double bond in the fatty acid chain, creating a lipid radical. That radical is highly reactive. It immediately bonds with dissolved oxygen to form a peroxyl radical. The peroxyl radical abstracts a hydrogen atom from an adjacent unsaturated fatty acid, producing a primary lipid hydroperoxide and a new lipid radical that continues the chain. At frying temperatures above 150 degrees Celsius, these hydroperoxides decompose into alkoxy radicals that undergo homolytic fission. They break apart, generating secondary lipid oxidation products. The aldehydes 4-HNE, 4-HHE, MDA, and acrolein, as well as trans fatty acids, polar compounds, and polymerized triglycerides. The critical point is that this chain reaction doesn't terminate when the oil cools. It slows down, but the radical species and hydroperoxides that form during heating remain in the oil. The next heating cycle starts not from zero, but from an already partially degraded starting point. Each successive use pushes the oil further along the degradation pathway. A study measuring polycyclic aromatic hydrocarbon content in sunflower oil at different stages of use found fresh oil contained 64 Fe6 microgram PGAs of total PAHs. After a single boiling, 134.56 micrograms. After repeated boiling, 235.98 microgram kgs. More than 3.5 times the PAH burden of fresh oil just from the process of repeated heating. The aldehydes produced by this process, particularly 4-HNE, accumulate in foods cooked in degraded oil at concentrations 5 to 15 times above what toxicologists consider safe. They're absorbed through the gut, enter the bloodstream, and have been detected crossing the blood-brain barrier. Studies link chronic dietary exposure to 4-HNE to up to a 75% increased risk of Alzheimer's disease. The 68% cardiovascular risk increase linked to repeatedly heated oil consumption, published in the British Medical Journal, comes from exactly this mechanism. The aldehydes damage arterial endothelium, trigger inflammatory signaling, and accelerate atherosclerotic plaque formation. This isn't about a single fry. It's about what cooking oil becomes when you use it 3 or 4 times across a week. Home cooking with the same oil twice is much lower risk than commercial frying operations that run oil for hours across hundreds of servings. But the direction of the chemistry is identical. It's a matter of degree and duration. You know the oil has gone too far when it starts smoking at lower temperatures than it used to, or smells sharp and acrid rather than neutral. By that point, it's already significantly degraded. The better rule is to use fresh oil for high heat frying every time and reserve the once used oil for low heat applications like sautéing, where temperatures stay below the threshold for rapid oxidation. The oil that makes everything taste better is, by the time you've used it several times, a meaningfully different chemical substance. And you can't tell from looking at it. Grilled and charred meats, steak, barbecue, chicken summer. You grilled steaks on Saturday. The char marks were perfect, the fat rendered. Someone took a photo for social media because the grill marks earned it. There were leftovers, 2 steaks, some chicken thighs, a rack of ribs with smoke worked into every layer. Sunday you put them back on the grill to warm up because the microwave felt like a betrayal of the original effort. The heat comes up fast. The edges start to darken again. The smell is close enough to Saturday that it feels like a continuation of the same meal. It isn't. Chemically, it's something else. When muscle meat is exposed to direct high heat, temperatures above 150 degrees Celsius from charcoal, gas, or open flames, 2 separate classes of carcinogenic compounds are synthesized simultaneously through 2 completely different mechanisms. The first mechanism involves a surface condensation reaction between creatine, a compound that occurs naturally in muscle tissue, and free amino acids and hexose sugars that are released as the meat heats. At temperatures above 150 degrees Celsius, these compounds react to form heterocyclic aromatic amines, or HCAs. The most abundant HCA in Western diets is FIP, 2-amino-1 methyl 6 phenylimidazo 4,4-pyridine. Another common one is MAQX. Both accumulate primarily in the charred outer crust of the meat. Both are genotoxic. They're metabolized by liver enzymes into reactive intermediates that liver enzymes into reactive intermediates that form DNA adducts. The same physical attachment to DNA that causes mutations and initiates cancer. Animal bioassays have confirmed that chronic oral exposure to FIP and AQX induces lymphomas, hepatomas, and colorectal tumors. The second mechanism is pyrolysis of fat. When fat drips from the meat onto the heat source, coals, gas elements, or wood, it enters an oxygen-depleted zone at temperatures above 200 degrees Celsius and undergoes thermal decomposition. This generates polycyclic aromatic hydrocarbons, or PAHs. The most studied and most dangerous is benzopyrene, a PAH that rides upward with the smoke from the heat source and deposits directly onto the surface of the meat. That dark exterior you see on grilled meat isn't just char. It's a deposit of PAHs laid on top of a surface already rich in HCAs. Now here's the specific problem with reheating. Charcoal grilled chicken breast carries HCA concentrations in the range of 1.55 ngGg and PAH concentrations of 5 to 15 ngGg after the initial cook. If you return those leftovers to a grill or a hot skillet, you're not just warming them. You're running the synthesis reactions again from a surface that already contains concentrated carcinogens. The charred zones get recharred. The already darkened surface gets darker. The chemistry compounds. Research on re-seared steak finds HCA concentrations exceeding 5 ngG and PAH concentrations above 20 ngG, levels classified in the toxicology literature as extremely high. The method you use to reheat matters more here than with almost any other food. Gentle reheating, covered pan on low heat, steam oven, microwave, raises the internal temperature to the bacteriologically safe threshold of 74 degrees Celsius without generating enough surface temperature to drive HCA or PAH synthesis. The chemistry is temperature dependent. Stay below the pyrolysis threshold and you're warming food. Exceed it, and you're making new carcinogens on top of existing ones. Trimming heavily charred portions before eating is not paranoia. It's removing the most concentrated deposit of the compounds that do the damage. That black char on the surface of leftover barbecue isn't crust. It's chemistry you don't need to eat. Pizza. Processed meat toppings. Nobody is afraid of leftover pizza. It might be the most benign feeling leftover in existence. Cold pizza exists as a cultural institution. Reheated pizza is what you eat while standing in front of the open refrigerator at midnight. It is, in the hierarchy of leftover concerns, somewhere between harmless and genuinely satisfying. This is largely accurate, with a specific caveat that most people eating pizza would never think to consider. The problem isn't the crust. It isn't the sauce. It isn't the cheese in isolation. The issue is the specific combination of ingredients on a meat-topped pizza, particularly processed pepperoni and Italian sausage, subjected to repeated cycles of reheating at high heat. Pepperoni is a cured meat. It contains sodium nitrite as a preservative, the same preservative responsible for nitrosamine formation in bacon and hot dogs when exposed to high heat. When you reheat a pepperoni pizza in a hot oven at 400 Fahrenheit to get the crust crispy and the cheese bubbly, you're creating the thermal conditions that drive nitrite-nitrosamine conversion on the surface of those small, thin, high surface area slices of cured meat. The concentration is lower than what you'd get from refrying a full strip of bacon, but the mechanism is identical, and the dose is cumulative. A slice heated once, then the box reheated the next night, then again the night after that, adds incrementally to the total exposure. The cheese and animal fat on pizza compound this through a separate pathway. Repeated heating of saturated and unsaturated animal fats generates free fatty acids, lipid peroxides, and secondary aldehydes, the same family of oxidation products that make repeatedly heated cooking oils dangerous. Again, one reheat produces negligible amounts. 3 or 4 reheating cycles of the same pizza box at progressively higher heat each time to try to recapture the original quality produces meaningfully more. What differentiates pizza from pasta as a leftover is this specific ingredient stack. Pasta has none of these variables. No nitrite preserved meat, no high surface area fat-laden topping, no repeated heating risk. Pasta reheats cleanly. Pizza with processed meat toppings reheats with chemical footnote every time. The twist that makes this genuinely interesting. Research on PAH accumulation in repeatedly heated animal fats shows that saturated animal fats, lard, beef tallow, the fat in pepperoni and sausage, follow the same oxidation pathway as vegetable oils, just at a higher temperature threshold. The initial degradation is slower, but once you've crossed that threshold across multiple heating cycles, the chemistry is equivalent. Eat the leftover pizza. One slice, reheated once, is not a meaningful health concern, but the box you've been pulling from for 3 days, reheated at higher and higher temperatures each time because you're trying to get the crust crispy again, that's a different situation. There's also a cross-cultural note worth making. In most of Europe, pizza is not traditionally a leftover food. It's ordered to be eaten immediately, and the idea of reheating it the next morning is considered somewhat alien. The American relationship with leftover pizza, the cold slice eaten directly from the box the morning after, or the slice aggressively re-crisped in a skillet, is culturally specific. It's also the behavior that most closely approaches the repeated high-heat reheating scenario. The food didn't change. The habit around it created the risk. The pizza is fine. The habit is the variable. Seafood, you know the smell. Leftover salmon reheated in a shared office microwave is a social event in the worst possible sense. Everyone in a 30-foot radius becomes aware of it simultaneously. The person who did it either doesn't notice or has decided not to care. The smell is distinctive and difficult, and it lingers. You already know not to do this. What you probably don't know is that the smell is chemically informative. It's telling you something accurate about what's happening to the fish. Seafood contains among the highest concentrations of omega-3 polyunsaturated fatty acids in the human diet. EPA, eicosapentaenoic acid, and DHA, docosahexaenoic acid, are the specific long-chain omega-3s that give fish most of their cardiovascular and neurological benefits. They're also structurally among the most chemically fragile fats in existence. EPA has 5 double bonds. DHA has 6. Every double bond is a site of oxidative vulnerability. The more double bonds a fatty acid has, the faster and more readily it undergoes lipid peroxidation when exposed to heat and oxygen. This is why the PUFA oxidation pathway that makes repeatedly heated vegetable oils dangerous runs faster in seafood than in almost any other food. The auto-oxidation chain reaction initiates more easily, propagates more rapidly, and generates oxidation products at lower temperatures and in shorter time periods. The specific aldehyde produced from omega-3 degradation is 4-hydroxy-2-hexanol, or 4-HHE, the omega-3 equivalent of the 4-HNE produced from omega-6 degradation in vegetable oils. Same mechanism, same class of reactive mutagenic aldehyde, same link to DNA damage, cardiovascular risk, and neurological inflammation. The research literature places repeatedly reheated seafood in the moderate PAH range, 1 to 5 ngGg, compared to low levels under 0.5 ngGg for gently reheated fish. That difference represents the measurable output of running the oxidation reaction twice. The smell of reheated fish isn't just odor compounds degrading. It's the specific volatile byproducts of omega-3 oxidation becoming airborne. Your nose is detecting the chemistry correctly. What makes seafood specifically worth understanding here is the nutritional irony. The omega-3 fatty acids that make fish one of the most recommended foods in clinical nutrition are the same compounds most sensitive to heat damage. A piece of salmon reheated once, gently at low temperature, oven at 275 Fahrenheit, covered for about 15 minutes, warms through without significantly driving the oxidation reaction. The EPA and DHA remain largely intact. The lipid profile stays close to what it was after the original cook. The same salmon reheated in a hot skillet or microwaved at full power for 2 or 3 minutes drives the fatty acid degradation significantly further. The omega-3s leave first. What you're left with after aggressive reheating is a food that smells like fish, has the texture of fish, and provides the protein of fish, but has lost a meaningful portion of the fat profile that made it worth eating, and has produced, in exchange, a measurable quantity of reactive aldehydes. There's also a timing dimension that doesn't apply to most other proteins. Seafood leftovers should only be refrigerated for up to 2 days before eating, not the 3 to 4 days that applies to poultry or red meat. The omega-3 oxidation pathway continues slowly even at refrigerator temperatures because these fats are so structurally vulnerable. A piece of salmon at day 3 in your fridge has already been oxidizing for 72 hours before you put it back in the microwave. The reheat doesn't start the problem. It finishes it. The smell isn't rude. It's a chemical report, and it's usually accurate, microwaving in plastic containers. This one isn't about the food at all. It's about what's holding the food. You have a takeout container, probably polypropylene. That's the slightly translucent, rigid plastic that makes up most microwave-safe containers you've ever owned. Maybe a reusable meal prep container you've had for a year. It's labeled microwave safe. You've used it dozens of times. You put it in the microwave, set 3 minutes, and walk away. The food gets hot. The plastic doesn't melt or warp. Everything looks exactly fine. Inside the plastic, during those 3 minutes, something significant happened. Plastics are not inert substances. They are long-chain polymer molecules combined with a variety of chemical additives, plasticizers that control flexibility, heat stabilizers, slip agents, antioxidants, colorants, UV blockers. These additives are not chemically bonded to the polymer backbone. They're dispersed throughout the material, held in place by weak physical interactions, not covalent bonds. Under the thermal stress of microwave heating, which generates intense localized heat, particularly where the food contacts the container, the polymer matrix destabilizes. The additives gain mobility and migrate toward the surface. When that surface is in contact with food, especially food that contains fat or has an acidic pH, the additives cross the interface into the food. The primary chemical migrants of concern are bisphenols and phthalates. Bisphenol A, BPA, is structurally similar enough to 17-beta estradiol, the dominant human estrogen, that it binds directly to estrogen receptors in human tissue. It disrupts hormonal signaling, interferes with reproductive development, alters metabolic regulation, and has been linked epidemiologically to hormone-dependent breast and prostate cancers. When manufacturers substituted BPA with alternatives like bisphenol S and bisphenol F to market containers as BPA-free, toxicological testing found that the substitutes showed similar or worse endocrine-disrupting activity on mammalian cell systems. The marketing changed. The underlying chemistry did not. Phthalates, plasticizers added primarily to polyvinyl chloride and related plastics, leach rapidly under heat and have been linked to anti-androgenic effects, reduced sperm count, birth defects, and insulin resistance. Then there's the physical particle release. In 2023, researchers at the University of Nebraska-Lincoln conducted a controlled study of FDA-approved polypropylene baby food containers and reusable polyethylene pouches. They filled the containers with deionized water and 3% acetic acid to simulate acidic foods and heated them at full microwave power for 3 minutes. The quantitative results were extraordinary. Some polypropylene containers released up to 11 billion nanoplastic particles, smaller than 1 micrometer, and 4.22 million microplastic particles, 1 micrometer or larger per square centimeter of plastic surface, not per container. Per square centimeter, to test biological toxicity, the researchers exposed human embryonic kidney cells, HK293 T cells, to the actual particles released by the microwave containers. At a concentration of 1,000 micromillims over 48 hours, 76.7% of the kidney cells died. After 72 hours, mortality reached 18%. The proposed mechanism is that while larger microplastic particles may be too big to enter individual cells, nanoplastics, particles under 100 nanometers, are small enough to be internalized by human cells through endocytosis. Once inside, they induce oxidative stress, disrupt mitochondrial function, and trigger apoptosis, programmed cell death. What makes this different from simply eating food stored in plastic is the role of heat as an accelerant. Cold storage in plastic releases some leaching, but at slow rates. Microwave heating concentrates the effect dramatically. Higher temperature, higher migration rate, more particles released per unit time, particularly in the presence of fat or acid, both of which are common properties of the leftovers most people actually reheat. The solution is genuinely simple: glass or ceramic containers. Every time. The microwave itself is not the problem. Non-ionizing electromagnetic radiation at 2.45 gigahertz cannot break chemical bonds or damage DNA, and microwaving often preserves heat-sensitive nutrients better than prolonged stovetop heating because the cooking time is shorter. The problem is the container, and it's the one variable in this entire video that you can change tomorrow morning without any trade-off. Whatever you're reheating, the most important health decision you make in that moment might be which container you put it in. Burned toast and high-heat starchy foods. This is the least dramatic entry on this list and possibly the one most people will dismiss. It's toast. You burned it a little. You scraped the black part off over the sink. Everyone does this. It's practically a universal technique, and ate the rest. The scraping felt like due diligence. Problem handled. The problem wasn't handled. What you scraped off the toast and into the sink was a concentrated source of acrylamide, the same compound formed in French fries, the same Maillard reaction product, the same liver-metabolized precursor to glycitamide, the same mechanism of DNA damage. Acrylamide is not specific to deep-fried potato products. It forms in any starchy food that undergoes high temperature, low moisture browning. Bread, when toasted, undergoes this reaction on its surface. The crust of fresh bread already contains baseline levels. Toasting drives the surface temperature above 120 degrees Celsius and strips moisture, running the Maillard reaction. The darker the toast, the higher the concentration. Research has quantified this specifically. Toasting bread for 3 minutes at standard settings produces acrylamide content of approximately 31 micrograms. Toasting the same bread for 5 minutes produces 118 micrograms. That's nearly 4 times the concentration from 2 additional minutes. The relationship between color and concentration is not linear. It accelerates as browning progresses. Because the reaction produces intermediate compounds that also serve as reaction precursors, compounding itself, the scraping technique doesn't solve this for a specific reason. Acrylamide is water-soluble and migrates inward from the surface into the bread matrix as the Maillard reaction progresses. The black exterior you remove contains the highest concentration, but the browned layers beneath it are not clean. You remove the worst of it. The rest came with you. What makes burned toast distinct from French fries on this list is the psychological profile of the food. Nobody thinks of toast as a cancer-adjacent food. Fries are fried. They feel like they should come with a health disclaimer. Toast is breakfast. It's made in 30 seconds. It's the food you eat when you're barely awake, on the counter while you're getting ready, not thinking about anything at all. The casualness with which burnt toast gets eaten every morning without scrutiny is exactly what makes it worth including. The differentiation from just eating bread is entirely about heat level and surface moisture. Standard bread at room temperature has negligible acrylamide. Golden brown toast has a small but measurable amount. Dark brown toast has more. Jet black toast has quantities that would be regulated if they appeared in processed food. This is not an argument against toast. Golden brown is genuinely acceptable. But the toast you burned and scraped and ate anyway, that wasn't a neutral decision. It was a small, invisible chemistry event that you ate for breakfast. Reheated rice and the hidden bacterial toxin. This entry is different from everything else on this list. It's not about chemical carcinogens produced by heat. It's about a toxin that forms before you reheat, that heat cannot destroy, and that you then eat, warm and unsuspecting, convinced that cooking it again made it safe. You made a large pot of rice on Monday. You put the lid on and left it on the counter to cool. An hour later, you put it in the fridge. Wednesday night, you reheat a bowl of it in the microwave, steaming hot, and eat it before a meeting. An hour later, your stomach decides to make itself the main event of that meeting. What happened in the pot between Monday night and Wednesday isn't visible. You can't smell it. The rice looks the same. But inside that pot, during the time it spent cooling on the counter, a bacterium called Bacillus cereus woke up and started working. Bacillus cereus is a spore-forming bacterium that naturally contaminates uncooked rice grains from soil contact during agricultural production. Its spores are remarkable objects. They are engineered by evolution specifically to survive conditions that kill everything else. Standard boiling, steaming, and even pressure cooking temperatures do not destroy Bacillus cereus spores. They survive the entire initial cooking process intact. When the rice begins to cool, those spores detect the change in thermal environment. In the temperature range between about 20 degrees Celsius and 45 degrees Celsius, which includes the room temperature of most kitchens, they germinate into vegetative cells, which double their population approximately every 20 minutes at optimal temperatures. Once the bacterial population exceeds about 100,000 cells per gram, Bacillus cereus begins producing toxins. The one relevant here is called cereulide, an emetic toxin that the bacteria synthesize directly in the food as they grow. Cereulide is a small ring-shaped peptide molecule. It is, by any measure, a remarkably robust compound, stable across a pH range of 2 to 11, which covers everything from battery acid to bleach, and it is heat stable at 121 degrees Celsius, the temperature of a pressure cooker, for up to 90 minutes without being inactivated. This is the critical fact. When you reheat that improperly cooled rice to piping hot, well above the 74 degrees Celsius threshold needed to kill bacteria, you kill every Bacillus cereus vegetative cell in the bowl, but you do not destroy cereulide. The toxin was made in the food while it sat cooling. Reheating kills the bacteria. The toxin stays. You eat the toxin. 30 minutes to 6 hours later, you experience the rapid onset vomiting that cereulide is named for in the clinical literature. What makes this different from just bad leftovers is that the food will seem fine. Properly reheated rice looks, smells, and tastes like safely reheated rice. There is no sensory signal that something is wrong. The bacteria are dead. The toxin is invisible. The only thing that would have prevented it was cooling the rice quickly enough that the bacteria never had time to manufacture the toxin in the first place. The FDA food code specifies the cooling protocol for exactly this reason. Cooked food must go from 57 to 21 degrees Celsius within 2 hours, and from 21 degrees Celsius to 4 within 4 additional hours. For rice, this means dividing it into shallow containers immediately after cooking, no deeper than 2 inches, to maximize surface area and dissipate heat rapidly. It means not putting the lid on a large pot and leaving it on the counter. It means not placing a warm pot directly in a crowded refrigerator where the insulating mass of cold food will slow the rice's core temperature drop to a crawl. Reheated rice made from properly cooled, properly refrigerated rice is safe. The problem is the specific sequence of events most people actually use. Cook a big pot, cover it, leave it to cool at room temperature, refrigerate it hours later, reheat it days after that. That sequence is a Bacillus cereus cultivation protocol, and reheating cannot fix what cooling failed to prevent.